and in that state you would have the dot moving towards the right. So F goes to this production, the dot should move one position. So F goes to bracket, then dot, then E. This is one production. And since E is on this E is directly to the right of the dot, so you must afford to put the E production another E production that would take you to this side. So you are taking care of this production, right? This production, and you are moving a dot to the right. Done? Fine? Okay. So let us complete this state. So this is another state that we had been talking about, and it had E goes to E plus dot T. Please try to concentrate, otherwise you will get confused. E goes to E plus dot T. And then you had T goes to dot T star F, because you are taking care of this T, and then taking care of productions that has this T on the left hand side. Then as usual, you are adding T goes to dot F. Then you need to add something for this F. F goes to dot bracketed E, and you need to add another one. F goes to dot num, right? So this completes all the items of this diagram. And as usual, we had decided yesterday that there must be transitions out on T, F, left parenthesis, and num. Now let us join them. So in state number 4, we see in state number 4, we have E goes to, okay, in this state number 5. In this state number 5, we have this E going to, F dot. So when we move on a F, this transition must go something like this. It's like a circuit diagram on F, right? Because here, by virtue of this production, the dot was on the left of F. So once you consume F, once you take this path and decide to push a F, remember that when you are pushing a F, that means you have already reduced, and F is the left hand side of the production. So the dot from the left of F should move to the right, and the state that has this item with the dot on the right of F is this state number 5. So this path, let us complete this path. This path goes here, right, on F. So what will be the path on T? That we'll see later. We have to add this state, and we'll find that, okay, this is the path that should be taking me to T, right? So we need to draw a state for that. Right now we have not drawn. Okay, what is the path that takes you on a left parenthesis? It should take you to the state that is responsible for the left parenthesis, right? And that state is this one, left parenthesis. Okay, now what is the state that takes you to num? Here, it is where it takes you to num. Ball. I'm just completing yesterday's picture.
F2, sir. Sir, that one, sir. We are going from state 2 to through E. Sir,
state
scroll
2.
Down. Yeah, state 2 through E we are going to, sir. It will be F2, then the dot will be after E, right?
After E, I have given after E. Oh, I have mistaken.
Okay.
It will be after E. Yeah, it will be after E. Yeah. Yes, thank you. Because before E was already there, right? So once you consume a E, it will be after. Sorry, this was not the production. The production we are interested in is here, right? So F goes to bracket, then dot, then E. So when you push a E, the dot should go to the right of this E. And that is why this dot is here, right? Is it okay now?
Yes, sir.
Okay. So on E we have seen, and on T, for T we have to design a state that would take you from T, and that T should take care of all the productions that has a dot on the left of T. So what is the production that has a dot on left of T? This is the production. E goes to E plus dot T. This is one production. And another production is T goes to dot T star F. These are the two productions. So we need to go to a state with these two productions, right? and we need to move the dot. We need to move the dot to the right. So it is E goes to E plus T followed by a dot, right? And the another production should be T goes to T followed by a dot plus F, right? Star F, sorry. Followed by a dot star F. Now is it okay? Please check. Now this state, so let me erase this. So the transition on T looks like this. Okay. Now this state is very straightforward because the dot is on the left of the asterisk sign, the multiplication. So it should directly take you to the state that we designed here, that takes you from state number 4 to some state on a star. So here also you will go on a star. That is simple. Understood? So once you get a star from this state, you immediately have this production that is a member of this state, right? And that completes this state, right? Now let me name the states so that you have a parity with the book. So you have this as state number 6, name this as state number 7, and name this as state number 8. Okay, and in your book you have dealt with, when you talk about the open parenthesis, then there must be a transition on right parenthesis, a pure shift, because it's a terminal symbol, and it will be shifted like this. F goes to bracket E and then the dot. Now see, in this state the dot is the rightmost symbol. So this state, if you name is as state number 9, is a reducible state. A whole reduction should take part from this state, right? So once you reach 9 through a tour in your diagram, that means you are now in a position. That means if you think of if you think of the whole tree, you are in a position inside the tree, in a sub position, in a sub root, where everything has been expanded. Whatever you have in bracket E and bracket, whatever you have even below this E, everything has been expanded, and now you are in a position to reduce the whole thing to F. So that is the characteristics of state number 9, because the dot is at the rightmost end, and you have only one production. There is no such conflict going on here, right? Now here in this state, you have state number 6, you have the dot preceding the plus. So you must go to a state whose LR item looks like E goes to E plus dot T. And here you have something like that, right? So on a plus, you should be going to somewhere like here. So on state a plus, yeah, you should be going to this state, because this state has the LR item that has E goes to E plus dot T. That means you have pushed a plus. The dot has moved to the right. Here the dot was on the left of plus, right? So this is a transition on plus. So you have done a transition on plus. So more or less you have done everything. And what are the transitions out of state number 8? So this is state number 8. What are the transitions out of state number 8? We decided yesterday that the two transitions must be the left parenthesis and on number, right? So num goes straight forward to here, because this is the only state responsible for consuming a num. So the dot is on the left of num. Here the dot is on the right of num. So you push a num and go here. And the state responsible for taking a left parenthesis is state number 2, that we discussed elaborately in last class. So it should go on a left parenthesis. Very simple. Okay. Also, there is a transition that looks like T goes to, so let me mark this transition, that looks like T goes to dot F, and there is another state that has T goes to F dot, right? So on a F, I must be able to move here, right? So this state must be able to go to this state on a F, right? Yes or no? Yes or no? Is it clear? Now, from state number 2, you can see that you have two transitions. E goes to dot T, and you have another transition that says that, okay, you have okay, E goes to dot T. maybe I missed a transition in this state. Let me add this transition. That's why it's not matching. So F goes to, so E goes to dot T, E goes to dot E plus T, fine. Then T goes to dot F. So you should be having another transition here. T goes to dot T star F, right? Now, by virtue of this production and this production, you must be able to make a transition on T, and that should be something like this. On T, you should be able to go here. Agreed? I missed that transition while I was designing the LR items. So this state number 2 has F goes to bracket dot E. Since E is on the right of the dot, I must take care of all the transitions that has E on the left. So this is one transition. E goes to T was the transition. So I must start with E and put a dot because nothing has happened till now. I must also add E goes to E plus T, put a dot in the front. Similarly, as you have a T on the right of the dot, you must take care of the T transitions. So we had two T transitions, right? We had two T transitions, 1 and 2. So T goes to F and T goes to T star F. So I had already added T goes to T goes to F, put a dot on the left because nothing happened till now. And I forgot to add T goes to T star F, right? So if it is becoming clumsy, then I can manage to add this like this. Okay, let me add this clearly. So since T is on the left of this dot, I must add T goes to F, this transition, and put a dot at the leftmost because to indicate that nothing has started. I must also add another T transition that had T on the left. So T goes to T star F. So we must add T goes to T star F and not forget to put the dot at the leftmost, right? Now, once you have that, if we see that F is on the right of, here we can see that F is on the right of the dot. So I must take care of the F transitions from our grammar that has F on the left. So we have two transitions that has F on the left. So F goes to E and F goes to num. So F goes to E and F goes to num. And we must not forget to place a dot at the leftmost. So this completes all the LR items right now. Is it okay? Yes or no? Tell me yes or no. So I have added all the items. And we have a state here that takes you on num. That takes you on num like this. And that state is responsible to have a transition on num. So we are only interested in this transition where you had a dot on the left of num. So I'll be adding f dot num and put a dot here to indicate that this state is the first state that I should start working with by pushing a num, right? By pushing a num. And this is how it looks. So by virtue of these two productions, I must be able to move a T and move to state number 4, right? Because in state number 4, I had E goes to T dot. So that means by virtue of this LR0 item, if I take a T by this path, then I have this LR item, the upper LR item. And if I take this transition and take a T from this state as I'm doing, I'll end up in this transition, right? I hope I'm not missing anything more. And this is the whole picture, right? This is the whole picture.
Sir,
yes.
On state 8, we have a transition on F. On state 8.
On state 8? Where is state 8? Okay, let us name this state as state number 10. On state 8, yeah, state 8, we have transitions on, we had a transition on F, right? Yeah. We had a transition on F. Is it the state that we had a transition on F? No. We had a transition, we must have a transition on F. And if we have a transition on F, we must go to a state that has T goes to T, that must go to T goes to T star F dot, right? On F. T star F dot. So let us draw a state. Very good, Sumit. So we must have another state that has, if we want to make a transition on F, That means this dot should move to the right in this state, right? So it should be T goes to T star F dot, right? And let us name this state as 11. Now, I hope this is the whole picture, right? So in this whole picture, if you are draw the picture properly, I could not draw it properly in this board. So what you can do is you can apply you can just apply your to check the state diagram's responses, and it inherently contains all the pushes and pops. It contains all the pops by virtue of saying that we move backward. So for example, you take the string that looks like this: 1 plus 2 plus 3. Intentionally don't take star and brackets right now, and check how your state machine works. Or you can do something like 1 star 2 plus 3 and check how your machine works, right? So once you see a 1 from state number 0, you must go to state number 1, and you find that, okay, it is if goes to num, so it must be reduced. Trace back to state number 0. That is what I mean. Trace back to state number 0. Now once you trace back to state number 0, it means that state number 0 is on the top of stack, right? The same thing that we talked about in the last class. So state number 0 is on the top of the stack. And what was the left hand side of the production that you used to reduce? It was F goes to num. So you need to go to the section of your table and find out what is 0 comma F. And if you understand properly, 0 comma F is nothing but you have to reduce with uh, this you have to follow this line, right? So you have to follow F and go to T dot F star. And why do you go to T dot F star? Because you had a LR0 item to start with in state number 0 that was telling that, okay, it is T goes to dot F. And then this state becomes a reducible state, and then you decide to reduce with T goes to F. Go back to 0 like this. This is your going back path. And again, 0 is exposed on the top of the stack. And the left-hand side of the production that you used to reduce was T. You must go to the go to section of the table to find out the entry of the state that is exposed, and the left-hand side that is T. And you find that, okay, we must reduce by T. Yeah, you must follow that path again, right? So this is how your state machine works. So we must not repeat because we don't have time. I hope everybody has understood. I took enough time to make you understand, right? Okay, I also was talking about that there are two interesting states where you have conflicts. Now, can you say what are the states that you have conflict? What are the states that you have conflict?
State 4.
State 4. Why state 4? Very good. Why state 4? Because state 4 has a completely reducible production with dot as the rightmost symbol. And also it has another item, sorry. It's not a production because it has dots. So it has another item that has a dot in between, right? So whether to shift on a plus like this and move to 8, or to reduce by E goes to T and move back to state number 0, that was a conflict that we termed as SR conflict. And we said that this can be mitigated if this grammar is helpful and it allows you to mitigate that problem. Then you can mitigate with the concept of follow sets. So if you go to this grammar, can you tell me what are the follow sets? Follow of let me say how many non-terminals you have? S, E, T, and F, right? So follow of S, follow of E, and follow of T, and follow of F, right? So you remember how to calculate the follow sets? It was mandatory to put the right-hand marker in your follow of the start symbol, right? That is what you have done. And follow of F, how can you calculate follow of F? Tell me, how can you calculate follow of F?
Sir, follow of T.
Follow of T. So follow of T, how can we calculate? You can see that it has a star. Fine, it has a star. Follow of T has a star.
Also.
And
because
why class?
Follow of
why
E
class?
will be included. Follow of E.
Union follow of T. Follow of E.
Yes.
Start,
So tell
start
me,
in the-
very good, very good. So what are the elements of follow of E or follow of T and follow of F? Tell me. So what follows E? First of all, is plus follows E. Plus
The
follows E.
closing parenthesis.
The closing parenthesis follows E. Fantastic. And what
And the
else
end
follows E?
marker.
And the end marker. Why end marker? By virtue
Because
of production
A
number
for
0.
T.
Yes,
Yes.
by virtue of production number 0. So if you have an input string and you start with that production, then it should be there, right? The starting marker should be there. So the end marker, not the start marker. So you have plus, then you have the right end marker, and then you have a right bracket, and then you have the end marker. So include everything that you have in follow of T, right? That is simple. Plus, and then follow of T extra symbol
Star.
is star, right? And then update follow of F. So this is the follow set information that you have. So these are the symbols that can follow S, E, T, and F under all circumstances, right? So you are not talking about any special circumstances. So these are the follow sets, means these symbols can follow S, E, T, F in any circumstance, right? Okay. So how did I ask you to reduce this conflict? So this conflict can be reduced if and only if the follow set of the non-terminal that you are using, that you would like to use for reduction, first of all, out of these two out of these two items, LR0 items, this is the only production that would be reduced if you take a reduced decision, because you cannot reduce this, right? So if you go for a reduced decision when you are in state number 4 and you are seeing a star, I term that as a look ahead symbol. That is the symbol that you can see. So what is the difference between a look ahead symbol and when you say that I am not using any look ahead? There is actually no difference, because you are scanning the next symbol. The main difference lies when you say that I am using star as a look ahead. It means you consume star and then take a decision. And when you say that I am not using star as a look ahead, that means you are not deciding on star, right? That is the only difference. Anyways, you are always able to see the next symbol by virtue of the shift movement. That is what you can always see. But when you are going to take a decision whether to reduce or not, that means that you must consume that symbol and take a decision, right? And if it doesn't match your decision, then again push back the symbol to the input. The same concept that we talked about in our lexical analysis class, right? Okay. So if you want to reduce, so state number 4 had a confusion. We call that as a SR conflict, whether to shift or a reduce. When you see a star, right? So when you see a star, you can use this production, T goes to T dot star F and move to state number 8. Fine. That's a shift. But also by virtue of this LR0 item, you may also reduce, right? So when you reduce with E goes to T, that means you take off T from the stack, and on the symbol stack E is visible. So when if you decide that I will reduce, when I see a star, that means star is the symbol that you are actually expecting after a E, because E is now exposed. So the symbol that you expect to follow E is star. So you have to check whether follow of E has a star. In this case, in this simple grammar, follow of E doesn't have a star. Since follow of E doesn't have a star, then you say that okay, the SR conflict is resolved for shift. I'm not reducing, because there is no confusion on star. By star, I can take a smart decision to shift, because star is not hindering my decision to reduce, because star is not a member of follow of E. So given in this grammar, star can never follow E in middle of a sentential derivation. Got my point? So in middle of a sentential form, in middle of a derivation, what type of derivation? The derivation that uses, in bottom-up parsing, you are going to use the rightmost derivation in reverse. So when you are thinking of a rightmost derivation in reverse, a star is not allowed by the grammar, by this grammar G, to follow a E at any point of time. That means at no point of time you are expecting that star to be appearing in the input when E is on the top of symbol stack, right? So you can take a running note that if you can easily resolve SR conflicts by using follow sets and one symbol of look ahead, now that approach that makes the grammar what is called SLR1, right? So this was an example of a LR representation, LR grammar. When you add the follow sort of intelligence with LR, when you add this intelligence, decide to use one symbol of look ahead that I used here as star. You can use any of the non-terminals as one symbol of look ahead. At any of the point, if you feel that okay, there is a possible SR. So here also you have a possible SR conflict, right? You have a E dot and you E dot T, but here by construction, but by construction you say that state number 3, in state number 3 I also decide on the right end marker, right? So since you are giving that extra information that I also decide on the right end marker, if you see a right end marker you straightforwardly reduce, right? And that right hand marker is not interfering with the plus decision. Algorithmically you can say that follow of S doesn't have a plus. Yeah, follow of S doesn't have a plus. Follow of A has only the right hand marker. So if you frame the algorithm in this way, that if the follow of a non-terminal symbol, that is the left hand side of the production with which you are reducing, does not contain the look ahead symbol, you can reduce if you have reducible items like this. So these are reducible items. But if you have, then you cannot resolve the SR conflict by using the follow set concept. So if you can resolve SR conflicts of all states, yes, what state did you say that it has a conflict? State number 10. Yeah, state number 10. Yes, state number 10 also has. Yeah, it also has a reduce SR conflict, right? So it also has a SR conflict. Now let us see how this conflict can be managed on a star, right? So it moves out on a star. So since it moves out on a star, what type of decision can you take on a star? That you have to decide. Now this is a reducible state. So the question is, can you if you see a star, what type of decision can you take? Tell me, what type of decision can you take if you see a star?
Only shift, sir.
Yes, you shift. Why shift?
If star is not in the follow feed.
Yes, star is not in the follow of E. So follow of E doesn't have a star, so you decide to shift. So in this simple grammar, in this state diagram, what you can see is none of the states has a SR conflict if you apply the concept of follow sets to these LR0 sets, and such a grammar that can resolve its conflicts by using the concept of follow sets is called a SLR1 grammar. So the grammar in this example is a SLR1 grammar, right? Did you understand? So these type of grammars whose state machine conflicts can be resolved with LR0 items added with that, if you can use the concept of follow sets, then these type of grammars are called SLR1 grammars. So in this example, this grammar is SLR1 grammar. But this grammar in this example is not a LR0 grammar, right? It is not a LR0 grammar. Why? Because by only LR0 consideration of LR0 items, and if you do not consider the follow set applications, you have SR conflicts in these states, right? You have 3 states with SR conflicts. So this grammar is not a LR0 grammar. To solve conflicts, you need to have one symbol of look ahead. No look aheads is not going to help you. So you want to have a grammar, you want to have an implementation with one symbol of look ahead, and that is termed as simple LR grammars, and that is called SLR1 grammar. Got it? So in this example, this grammar is a SLR1 grammar. This grammar is not a LR0 grammar. Understood? Any questions you have? Hopefully you have no questions. Now let me write down a very important pertinent question that I think that should be coming in your mind. And that question is, what if the follow of a non-terminal, now which non-terminal? The LHS of the reducing production, right? That non-terminal. So what if the follow of that non-terminal contain an outgoing edge on a terminal that is a member of follow of that non-terminal? So here we were saved because none of these star, or this plus was a member of respective follow sets of the non-terminals S, E, T, and F. Now the question becomes, the problem becomes harder if the follow sets contain those terminal symbols. For example, what if the follow of S has a plus? So if you have a grammar which has follow of S having a plus, then the SR conflict of this state is not resolved. Do you agree? Yes or no? Okay. So generally follow of a non-terminal are all symbols that can follow the non-terminal in all possible contexts. So this is a general statement that we know. Follow of a non-terminal are all symbols that can follow that non-terminal in all possible contexts, right? Now we are going to use this idea to generate a new idea that I draw like this. I'm writing more today because you cannot see me. So the idea is that we can reduce the follow sets according to our context. So we can go for context aware reduced follow sets, because the general concept of follow set is, when you say that we have a follow of a non-terminal, it means all symbols that can follow the non-terminal in all possible contexts. In our state machine, the contexts are very well defined, right? Do you agree? The contexts are extremely well defined, and we do not need all the elements all the elements of the follow set of a non-terminal for deciding on transitions. So we can go for context-aware reduced follow sets. And what are those sets called? In compiler design, we have a name. Those sets are called look-ahead sets. So we do not need to accommodate all elements of follow sets, and we can work with smaller follow sets, and thus we can eliminate the chances of some symbol being in the follow set as well as in the look ahead, right? So anyhow, we are trying to manage to reduce that set such that our look ahead set is free of symbols that can actually follow that non-terminal in that context, right? Now things will become clear more if we do this. So how to do this? How to reduce this? How to reduce this? Try to think that what we can do is we actually can think of a production as as it moves along a path of the state machine. For example, we start with a production, and then that production moves along a path of a state machine. And along the path, we are going to consider only those terminals that can actually follow the non-terminal, right? That is on the left-hand side of a production. Because in case of a reduction, immediately after we reduce, the question that gives us the confusion was, immediately I go for a reduction, the left-hand side of the production with which we reduce is on the top of the symbol stack. And the symbol that we are seeing next in the input is some symbol that it should be there if it is in the follow set of the left hand side of the non-terminal, because we are reducing. And if we are shifting, no question of that to be in the follow set, right? So how do we do this? Let us go to this picture again. So let us think of paths that take you from state number 0 to say okay, from 0 to state number 10. So let us think of a path that takes you from 0 to state number 10. So what are the elements, what are the states that you visit from 0 to state number 10? If you start with, for example, you start with E, right? You start with pushing a E on the stack. That means you are in the middle of a derivation, right? Because in state number 0, you always start with F goes to num in bottom-up parsing. So that means in the middle of your derivation, you have returned to state number 0, and now you are trying to reduce with E goes to somewhere, right? So this E means pushing the left-hand side of the production that has E. So we have two productions that has E on the left-hand side. So we are trying to reduce either by this production or by this production, whatever it is. We do not know till now. But we have this path that takes us from 0 to 3. Then you have this path that takes you from 3 to 7. And then you have this path that takes you from 7 to 10. So along this path, 0 to 3, and then 3 to 7, and then 7 to 10, what you have is you have E, you have plus, and you have T. That means you are moving from state number 0 to state number 10. That is one path that takes you to state number 10. But you have other paths that take you to state number 10. Like you have, like your string doesn't start with a num, rather it started with a bracket, and you have this bracket. So from 0, state number 0, you go to state number 2. And then from state number 2, you go to state number 6. Then from state number 6, you go to state number 7. And then from state number 7, you go to state number 10. So let me draw this. You have two options. You start in state number 0, and you want to go to state number 10, right? Along the path. So you have, this is one possible path via state number 3 and state number 7. And this is one option. The other option is go to state number 2, go to state number 6, then go to state number 7, and then go to state number 10. Right? So how to collect look aheads at each step such that you have a set of look ahead to look for in state number 10. So if I want to build a set of look aheads for some non-terminal, for some elements of state number 10, the technique is, how to do this is, you go on collecting look ahead symbols for that non-terminal along the path and go on adding them in this set. Likewise, you go on collecting the look ahead symbols for a particular non-terminal along this path and go on adding these sets. Then take a union of these two paths and you have a selection of look ahead symbols, right? Now, the only important terminals that are going to help you out are actually those terminals that follow the non-terminal, right? Preceded by a dot. So when you have a dot, that non-terminal, see, what is the meaning of this? The meaning of this is we are interested in the format. You have a dot followed by a non-terminal N and then followed by a terminal symbol. We are interested in such a configuration. We have a dot, we have a non-terminal, and we have a terminal symbol, right? Now, why we are interested in this? in case of a reduction by this non-terminal, in the next sequence, the dot is going to move to the right of the non-terminal, and you have a transition on this non-terminal, and this symbol is now becomes very important, because this symbol contributes to resolution of the SR conflict. So if we say that this symbol can actually follow this non-terminal, then we'll go for a reduce. And if this symbol is not contributing to the reduction process, then we say that, okay, this symbol doesn't contribute to the reduction process, and so we are going to apply this for your shifting operation, right? So how to do this? Let us take an example. The very fast production that we have in our grammar is S goes to E, right? And as usual, you are going to add a right hand marker to E, and in the very fast LR0 item, you have S goes to dot E followed by the end of input symbol. Now, if you go through this construction, this was our LR0 item, right? The LR0 kernel item. I told you that this was the LR0 kernel item. And from this item, we built out all these items. And having an information of all these items, we build out all the other states. So this was the kernel item that we started with. S goes to E, and we put a dot to indicate that we have not yet started any proceeding. So we can convert that LR0 items to this LR1 item. Now I am talking about LR1 grammars, right? So we talked about LR0 grammars. We talked about SLR1 grammars. Now we are talking about LR1 grammars, because we are trying to think, what if we cannot solve the SLR1 case with follow sets? What if the symbol that we are looking at to is belonging as a member of the follow set of a non-terminal, that is the left-hand side of the production that we are reducing with. So we are trying to make look-ahead sets that are somewhat smaller in size, such that we somehow can manage to eliminate a symbol that is creating a problem. And so we are talking about new set of items called LR1 items. And since as we started our whole thing with this kernel item, S goes to E with a dot at the left, similarly here, we try to say that this is the kernel item of all LR1 items. And here, what we are doing is you are adding an extra symbol, that is the end of input symbol for the kernel item, right? Now, this item will contribute to form other LR items, right? In a very recursive procedure, you can write a algorithm for that. But on the contrary, let us take an example of a production of our, for example, let us take this example. F goes to dot bracketed E. So that was one LR0 item. So previous LR0 item. An example is, what was the example? F goes to bracketed E with a dot to indicate that nothing has started yet. So this was a valid LR0 item in the previous example. Now, shall we convert this LR0 item to a LR1 item? Do we need to convert this to a LR1 item? The answer is no. We do not need to convert this to an LR1 item, because it doesn't contribute. Why? Because the dot is on the left of a terminal symbol. We are only interested in things where a non-terminal symbol has a dot on its left, because then only we are going to think of accommodating those productions that have this non-terminal symbol on the left of some other productions, right? So this doesn't contribute. So these type of LR0 items, we do not need to convert them to LR1 items. But these type of LR0 items, the LR0 item was, the equivalent LR0 item was, the kernel item was S goes to dot E, right? We need to convert this by adding the look ahead symbol. So here we have a look ahead symbol, and that look ahead symbol will let us take a decision whether to reduce with S goes to E. So this production contributes to form a LR1 item, and this is an LR1 item, right? So how does a LR1 item look like? So you can say that it looks like S goes to, so again our generic way of saying things in grammar notations. So this is one LR1 item, right? So the LR0 items look like this. There is a left hand side, there is a right hand side. For each such production, start with placing a dot as the leftmost point, and LR1 items looks like this, right? So you have a production S goes to alpha beta, dot is somewhere in between. The dot may be here, the dot may be here, the dot may be here. So to generalize, I have put the dot in the middle, it doesn't matter. And followed by D is the look ahead symbol, right? So an LR1 item looks like a production. So what was the production in this case? S goes to alpha beta, right? A dot and look ahead symbol. Now, do you have only one look ahead symbol? Not necessary. You may have more than one look ahead symbol. So this combination, this triple, gives you an LR1. Now I will show you how LR1 items are built at each step and how they are collected for a particular non-terminal. For example, let us talk about a particular non-terminal E. How for a particular non-terminal you start with a LR0 item, convert it to a LR1 item like this. You place the right hand marker and move to 3, and in 3 you again collect more look ahead symbols for E. In 7, you carry out the same process recursively and increase the look ahead set for E. Come to 10, and you have a set for look ahead of E that is expected to be of size less than or equal to the follow of E. Right? And for each such non-terminal, we have S, E, T, and F in our grammar. For each such non-terminal, you have to collect look aheads. So it's a collect algorithm, right? And build a look ahead set when you reach 10. Similarly, you collect look aheads and build look ahead set when you reach 10. If they differ, if these two paths differ, take a union. So you have a set S1 of look aheads for the non-terminal E. You have a set 2 of look aheads for non-terminal E along the path 0, 2, 6, 7, and 10. This is a collection of look ahead along the path 0, 3, 7, and 10. Now, if these are not same, take union and build this look ahead set. And you expect that look ahead set to be less than equal to the set of follow of E, because follow of E has all symbols that can follow E at any situations. But these two sets have only symbols that can follow E if you take this path, if you take this path. So you have a chance to eliminate certain symbols from follow of E, and because they are not required in the look ahead set for your decisions in the state table. Because this is a schematic representation of a state table, right? You go to 0, from 0 you go to 3, you go to 7, you go to 10, and all these decisions from 0 to 3, from 3 to 7, from 7 to 10, or 0 to 2, from 2 to 6, 6 to 7, 7 to 10, all these decisions do not require full-fledged follow of E items. They require a handful of items, and that is what we want to designate as look ahead symbols, right? So you start with the kernel item that looks like this, and in our case, the kernel item looks like S goes to dot T followed by the end marker, and we'll show you. I will in short write the algorithm and show you how to build the LR1 items. And in today's class, by talking about that algorithm, go through books, and you will understand. So the kernel item, the algorithm looks like this. Start with a kernel LR1 item. In this grammar, the kernel item is S goes to E right hand marker, because that is the tuple, right? The LR1, that is the triple, and don't forget to put a dot. So if you remember, S goes to dot E was the LR0 item. So the LR0 item and the LR1 item only differs in a look ahead symbol, right? Okay. So build a kernel item. Now the algorithm says that if you have a production, if you have a LR item that looks like S goes to alpha dot X beta, comma, capital C. If this is a LR1 item, it is very easy. Don't get afraid. Don't get confused. Easy. If it is an LR1 item, then take care of the non-terminal as usual, that is after the dot, and search for productions where that non-terminal X is on the left, right? So then for all productions of the form X goes to gamma, so all productions where X is on the left of the production, add LR1 items like, so what you have to do, you have to add LR1 items like X goes to gamma dot, comma, the first of this beta followed by this C. Now use your brains for 2 minutes. You will understand that this may look cryptic, but this is very easy to understand. So if you have, please concentrate for 2 minutes and you will understand everything. So if you have an LR1 item that looks like this, S is a non-terminal, it goes to alpha dot X beta, alpha beta as usual are strings from N union V star of your grammar. So everything is same, don't worry. X is a non-terminal, S is a non-terminal, and C is a look-ahead symbol. For example, this is the kernel LR1 item. So if this is one LR1 item, you begin with the kernel 1 item, the kernel LR1 item. Now for each such kernel items, the kernel item is generally a single item. So you start with this LR1 item, take decisions on this non-terminal, find out the productions in your grammar where the productions look like X goes to somewhere. Again, gamma is a string from N union sigma, N union V star. So these are strings of terminals and non-terminals in the most generic case. So you have to take care of this non-terminal, right? X. So find out productions that look like this and build LR items like X goes to gamma, give a dot, comma, first of beta C. Now what does first of beta C mean? First of beta C means what are the items that can follow X? So from this LR item, let me change the color. From this LR item, straightforwardly, anything that follows X must be in the first of beta, right? That is very simple. So by what do I mean by first of beta C? I mean first of beta and then C. That is, if beta is eventually nullable, that is, if beta is nullable, then the LR item looks like X goes to dot gamma C. So this is called direct inheritance. You started with a look ahead item of C, right? And you end up with that particular look ahead item of C. But if beta is not nullable, you go on adding the symbols with which beta can start with, right? Because the symbols with which beta can start with directly follows X. Understood? Yes or no? Yes or no? So if you understand this, everything will be very easy to understand. So we are building these look ahead symbols, we are building these look ahead sets step by step such that we can use that along the path of your state machine. So if this is one LR1 item where you say that S goes to alpha dot X beta comma C, where C is the look ahead symbol, it's a terminal symbol, it's a look ahead symbol. Then find out all productions with X on the left. And for all such productions, go on adding LR1 items that looks like this. X goes to gamma, put a dot on the left, comma, what are the look aheads for X? Whatever there is in first of beta C. Because in the previous LR1 item, you see that first of beta contains all symbols with which beta can start with. So those are the symbols that can follow X, fine. But C is also one symbol that was following X, right? So we want to include that symbol that can follow X. So let us see an example. For example, let us start with the kernel item. So if this is the kernel item, let us start with this. S goes to dot E. So this is the kernel item that I start with. This is the kernel item that I start with. So imagine that your alphas and betas are here, right? Imagine. So for imagining, I am using the red color. So here, both alpha and beta are nothing but epsilons. That is what you collect in your brains. Okay, now apply the algorithm straightforward. So I need to find out all productions that has E on the left hand side, right? From our grammar, I need to find out all productions that has E on the left hand side. And I find out that I have two productions, E goes to E plus T, and I have another production, E goes to T. Fine. So the algorithm says that for all such productions, I have two productions. Fine. For all such productions, you have to build LR1 items that look like this. So let us build one LR1 item. So how to build LR1 item? To build LR1 item, I have to put dots here. So I take these two productions that has E on the left hand side because I'm taking care of this E. Alphas and betas are epsilon in our case. So the first LR1 item that I built from this is, I give a comma and I say it is the look at symbols are first of beta C, beta is epsilon, so epsilon, and C was end of input marker. So this is the first LR1 item that I generate by using the kernel item. This was a kernel item, right? So this is another LR1 item that I now have, and that LR1 item is talking about an item that is the production E goes to E plus T. That's a production, a dot is here on the leftmost, a dot and a lookat symbol. And the lookat symbol is the left end marker of the string, right? Because first of epsilon followed by the end marker is the end marker. Okay, so you have this, and go on recursively finding out what else can be done. So, so what you can do is you can perform a recursive closure operation and find out more and more LR1 items. Okay, for example, you have this as a LR1 item. Now I will apply the recursive closure composition algorithm, and I will again apply the closure formation algorithm. This algorithm I will again apply to find out whether there are other LR1 items. So let me write down this LR1 item. So what was the item? It was E goes to dot E plus T followed by the left hand marker. This is the LR1 item that we generated, because first of epsilon left hand marker is the left hand marker, right? So we add, so what does the algorithm say? We add LR1 items that looks like this. So this E is on the left hand side of, so this E is on the right of the dot. So I take care of this E with this same production again, right? And then I mentally think of this string as alpha dot E followed by beta. So mentally my alpha is epsilon and beta is plus T. So what I do is I calculate first of plus T, and this is what we already have. So this is another LR1 item that I create from this LR1 item that I created from the kernel item. So I started with the kernel item, I created this item, and I applied that algorithm again. I thought of E goes to dot E plus T as alpha, E goes to alpha dot E plus T, and I mentally think that this plus T is beta. If this is beta and this is the right hand marker of your string, then I should add E goes to E plus T. Sorry, I forgot to give a dot. E goes to dot E plus T first of this. So the item now becomes E goes to dot E plus T, and the first of plus epsilon and right hand marker means you have plus and right hand marker. So this is the LR1 item that you have generated. Okay, similarly, you can apply this in similar fashion to generate E goes to dot T followed by the right hand marker, and also you can generate items like E goes to dot T plus. And see, these are two different LR1 items. Why? Because the production and the dot are same, but the lookahead symbols are different. Take a union to have E goes to dot T plus right hand marker. So this is one composite LR1 item that you have. Similarly, you can apply to you can use this as your start case, and since T is on the right of yes, somebody is saying something. Please concentrate for 10 minutes. I am leaving in 10 minutes. Don't worry. Okay. Now, these are hard things to conceptualize, so please pay attention. Things will become so easy for you. So let us take this LR1 item that we have generated right now, and okay, or this one. This is one which we created by taking union. So E goes to dot T, and these are the two lookahead symbols that we have, right? So T is on the right hand side. So I must list out all the productions with which T can start with. So I have T goes to T star F, and also I have T goes to F. So let us talk about this. So the algorithm says that, okay, build a LR1 item, place a dot here, think of an alpha. So think of an alpha and a beta. I think of these as the beta, and I list out that I already can inherit, that is plus and in the right hand marker. So this now becomes our application algorithm application point of view. So we add T goes to dot T star F followed by first of beta and the remaining symbols. So first of star F plus and this one, right? So this becomes a new LR1 item that looks like T goes to dot T star F and plus star. So this is another LR1 item that is what you actually generated from here. So go on generating LR1 items like this, and go on listing the LR1 items. And if you go through your Hollywood book, if you don't have time, I can just draw a single state picture that lists
Star
out.
plus.
Yes. What?
Star plus, not plus star.
Yes. What? Star plus. What was
Star
saying?
plus n marker. So in the first of star F plus n marker,
Yes.
there will be star plus.
Yeah. Star plus n marker. This star F is your beta, right? This star F is your beta. So first of star F, for example, first of star F is star, because star is not an epsilon. This is not a nullable one, right? So whatever first of F has, it doesn't count. It is star. And these are the two symbols that you have inherited. So you have star. These are the symbols that you have already inherited. Did you understand? Your beta.
So star will be in the front before plus.
That doesn't mean anything. This is a list of lookahead symbols. You even rewrite something like n marker plus star. That sequence doesn't matter. Your algorithm doesn't talk about the sequence, right, Rishi?
Okay, sir.
Did you get my point? The most important point is first of beta, and by first of beta C, the algorithm means that include first of beta, whatever you have in first of beta, and also keep the lookahead that you inherited. So here your beta is star F, right? So first of star F is always star, because star is not epsilon. So I am not worried about what are the symbols with which f can start with. That means I am not worried about first of f at all. I am not worried about this because, did you get my point? So this
Yes,
whole
sir.
thing always starts with a star. Now this sequence, this is actually a very good question. This sequence doesn't mean anything to you. It's a list of items. Did you get my point?
Yes,
So
sir.
for this, these are the lookahead symbols. So the moral of the story is this T, follow of T. In this grammar, your follow of T, what are the symbols in follow of T? Tell me. What are the symbols in follow of T? We just did this, right? In this grammar, the symbols in follow of T was plus, right and
Yes,
marker,
sir.
end and star, right? So for this particular path, there is a chance that you may get rid of that bracket, right? There is a chance, but we never know. We need to build more and more LR1 items. And for this particular example, you may land up with the set of LR1 items to be same size of the set of follow sets, right? So that doesn't prove that your approach is all a wastage, but it says that for this grammar, you may have the set of lookahead symbols same as the set of same size as the set of follow sets, but you may have complicated grammars where the lookahead symbols for a particular path actually becomes less than the follow sets of particular non-terminal symbols, right? So go back and follow your books and find out how to use those LR items for decisions. So I can just start with just draw a single state and make you try to explain. So as usual, this is your state number 0. There is no difference, right, with LR0. The only difference is you list out the lookahead symbols. So tell me what we started with. We started with H goes to E. We put a dot, right? We put a dot. Since E is on the right of dot, we need to take care of these two E's. E goes to E plus T. E goes to T. Since there is a dot on the left of T, we need to take care of these T's. T goes to T star F. T goes to F. Since there is a dot on the left of F, F goes to num and F goes to dot E, right? Now, so this was the state property as listed out as the LR0 items. For LR1 transition, state transition machine, you just list out the lookaheads that you have collected in state number 0. So for each state, list out the lookaheads for each non-terminal symbols, right? So here you have the right hand marker. You have here you have plus and then the right hand marker. For E, you have plus the right hand marker. For T, and state number 0, you have star, you have plus, you had the right hand marker. For T, you have the right hand marker, plus and star. I intentionally jiggled up with the sequence, Rishi. It doesn't matter, right? Okay. What matters is the list, the contents. And here also you have plus, then star, and then the right hand marker. Here also you have the star, plus, and right hand marker. So these are the look aheads that you have collected in state number 0. So when you move to this state, use those look aheads and collect any more look ahead that you may have. Then you go to another state, collect any more look ahead you may have, and then reach some state where you collect any more look aheads. But you can expect that going by this path, the look aheads that you collect, you can hope that the size of that look ahead set is less than or equal to the size of the follow set, right? Now, why do we need to, what is the moral behind the story? The moral behind the story is follow sets contain all symbols that can follow. But we need only those symbols that are creating a problem in these transitions, right? So we do not need all the symbols that can generally follow me. But I am just talking about only those symbols that may be creating a problem in these paths. So that size may be reduced, and in the act of reducing that, I may be eliminating certain symbols that were creating a problem, right? Such that I can take a decision for a shift or a reduce in a more smarter way. Now things will look heavy unless and until you go through books. So please go through books. I may require one more class on Monday. I will tell you whether it will be online or offline. I prefer offline classes. Simple 1 hour class on semantic analysis. I need to introduce that topic, and that will end things. Okay. Okay. If you have any questions, you may ask me. The problem with online classes is now I do not know who are there in my class and who are not. Okay, so I'm ending the class.
Okay, sir. Thank you, sir.
Yeah. Okay. Yeah. Bye.
Thank you, sir.
Yeah.
Thank you, sir.